Okay, let's talk about moles, molar mass, and something called Avogadro's number. So back when we talked about the 6 SI units, the 6 SI base units, there was a category for a quantity or an amount, and the SI unit for that was a mole. So what a mole is it's a unit for a specific number. And it's a big number. So 1 mole of anything equals 6.02 times 10 to the 23rd of whatever. So it's like a dozen. So people get freaked out and confused about what a mole is because this is a big number that people aren't very comfortable with. But a mole being 6.02 times 10 to the 23rd of something is the same thing as saying 1 dozen is 12. And that's not intimidating or scary to anybody because we know about this. We know when somebody says a dozen eggs, they mean 12 eggs. If somebody said they got a mole of eggs, that means that they bought 6.02 times 10 to the 23rd eggs. So this number, 6.02 times 10 to the 23rd, this is an important number. This is called Avogadro's number. And what Avogadro's number is it's the number of atoms in 1 mole. And remember, MOL is the abbreviation for mole, M-O-L-E. So the other piece here that we need to talk about is something called the molar mass. And what the molar mass is it's the mass of 1 mole of an element. Of 1 mole of an element or compound. So the molar mass of an element is the atomic mass, which we remember is found on the periodic table. So for example, if I ask you, what is the molar mass of carbon? You would look at the periodic table and say, well, the atomic mass of carbon is 12.01. So that means the molar mass of carbon is 12.01. The molar mass has a special unit because this is the mass, and we said it's the mass of 1 mole. The mass of 1 mole, that means the unit is going to be grams per mole. The unit for molar mass is grams per mole. So the molar mass of every element is the atomic mass on the periodic table. The molar mass of a compound is just the sum of all the masses in that compound. So if I said, what is the molar mass of water? I would say, okay, well, what's the molar mass of hydrogen? And I have 2 of them, plus what's the molar mass of oxygen? So I would say the molar mass of hydrogen, depending on what periodic table you use, I'm just for simplicity's sake gonna say it's about 1.01 grams per mole, and I have 2 of them, so that's 2.02 grams per mole. And then the molar mass of oxygen, again, just to be simple, I'm gonna say that's about 16 grams per mole. So 2.02 plus 16 means the molar mass of water is about 18.02 grams per mole. So we use molar mass whenever we're doing any calculations in chemical equations because we need this value to navigate calculations in chemical equations. So moles, molar mass, and Avogadro's number is very important. Another thing that we can do with Avogadro's number is we can use Avogadro's number to determine how many atoms we have. So 6.02 times 10 to the 23rd atoms or molecules, depending on what you're talking about, per mole. So now we have two new things that we've learned. We've learned Avogadro's number is 6.02 times 10 to the 23rd atoms per mole, and that the molar mass has a unit of grams per mole. So remember, anytime you see a unit with two units, like atoms per mole or grams per mole, you are going to use those as conversion factors in dimensional analysis. So let's do some examples because that's really the best way to explain this. So I'm going to say how many atoms of carbon are in 65.23 grams of carbon. Okay, so I always start out with a plan for how you're going to solve this. I'm given grams of carbon and I want atoms of carbon. So if I look at these two new conversion factors that I have Avogadro's number, which goes between atoms and moles, and I have molar mass, which goes between grams and moles, but I don't have anything that goes between grams and atoms directly. So my plan to solve this problem is I'm going to take grams of carbon, I'm going to convert it to moles of carbon, I'm going to take moles of carbon, and I'm going to convert it to atoms of carbon. I'm going to go from grams to moles using the molar mass. M, this big M, little m, is an abbreviation for molar mass. And then I'm going to use Avogadro's number to go from moles to atoms because I know that there are this many atoms in 1 mole. Again, you do not have to set up these dimensional analysis problems the way that I do. I'm just going to do it to be consistent with what's in your text and what's in the homework. So I'm going to say 65.23 grams of carbon. And I want to cancel out grams first. I want to go between grams and moles. So I want grams on the bottom and I want moles on the top. So where do I get the molar mass? Well, you get the molar mass from the periodic table. So you're going to look at the periodic table. You're going to find carbon. Carbon is number 6, and it has an atomic mass of about 12.01, and that is grams per mole. So now I've done my first step. I've gone from grams to moles. The next step is to go from moles to atoms. So I know I want moles on the bottom and I want atoms on the top. So moles will cancel. So to go between moles and atoms, it doesn't matter which element you have, you always use Avogadro's number. 6.02 times 10 to the 23rd atoms in 1 mole. Moles will cancel. Now I'm going to multiply across the top and divide by what's on the bottom. So I'm going to say 65.23 times 1 times 6.02 times 10 to the 23rd divided by 12.01. And I get about 3.269 times 10 to the 24th. So now I need to figure out how many significant figures should I have. Well, I'm using multiplication and division. I always use the number given to me in the problem. Remember, the molar mass and these are constants. They are exact numbers. They do not contribute to the number of significant figures. The number of significant figures in the problem is 4, so my answer should have 4 significant figures. So I'm going to say 3.269, and then I would round up. So I'm going to say 3.270 times 10 to the 24th. And again, my unit is atoms, or you could say atoms of carbon. So now we're using moles, molar mass, and Avogadro's number in dimensional analysis to figure out how many atoms of carbon are in 65.23 grams of carbon. And again, you do not have to do it the way that I do, but this is the way that I'll do it just to be consistent. So let's look at another one. So let's say how many moles of sodium are in 95.3 grams of sodium. Sodium is Na. So I'm going from grams of sodium to moles of sodium. So I want to go from grams to moles. And the way I go from grams to moles is by using the molar mass. And where do we get the molar mass? We get it from the periodic table. So you're going to find sodium on the periodic table, and you're going to find that the molar mass of sodium is about 22.98 grams per mole, depending on which periodic table you're using. So I'm going to start with what I'm given, 95.3 grams of sodium. I know I want grams on the bottom and moles on the top. And the molar mass of sodium is 95.3 grams of sodium in I said the wrong thing, 22.98. I put the mass up there again. The molar mass of sodium is 22.98. 22.98 grams per mole. Grams will cancel. You'll be left with moles. So 95.3 times 1 divided by 22.98. Your answer should have 3 significant figures. You should get about 4.15 moles, or you could say moles of sodium. So there's lots of different ways that you can go depending on what information you're given and what you're being asked. Okay. Let's do an example with a compound. So let's say how many moles of ammonia, ammonia is NH3, I would not expect you to know that. How many moles of ammonia are in 100.0 grams of ammonia? Okay, so I want to go from grams to moles. So I know I go from grams to moles using the molar mass, but instead of having an element now I have a compound. So remember, the way that we determine the molar mass of a compound is by adding up the molar mass of all the elements in the compound. So first I have nitrogen, and that has a molar mass of about 14.01 grams per mole. And then I have hydrogen, I have 3 of them, which I'm going to say is about 1.01 grams per mole. I'm going to multiply that by 3. So that's 3.03 grams per mole. So then the molar mass of NH3 is about 17.04 grams per mole. So you can't just look at the periodic table and get the molar mass for a compound. You have to get the molar mass of each individual element, and then based on how many of each of these you have, you can calculate the molar mass of the whole compound. So this little lower 3 here, this is called a subscript. This subscript tells you how many hydrogens you have. There's no parentheses here, so this subscript only applies to the element that it follows. If there was parentheses around NH and then a 3, that would mean you would have 3 nitrogens and 3 hydrogens. So we'll do lots of examples to look at more of these. But for now, this is the molar mass of ammonia. So now we're going to use it to convert grams of ammonia to moles of ammonia. So I'm going to say 100.0 grams of ammonia. And the molar mass of ammonia is 17.04 grams of ammonia in 1 mole of ammonia. Grams will cancel, so now I have 100 divided by 17.04. The answer should have 4 significant figures because 100.0 has 4 significant figures. So 1, 2, 3, and then I look here, I'm going to round up. So 5.869 moles of ammonia are in 100 grams of ammonia. So we use moles, we use molar mass to determine, to use as a conversion factor, because we're going to use this later when we're looking at more complicated chemical reactions. But for now, what you need to be comfortable with is calculating the molar mass of compounds by adding up the molar masses of all of the elements, using molar mass as a conversion factor, and using Avogadro's number as a conversion factor. You will be given Avogadro's number on an exam, and you will be given a periodic table to look up molar masses. So if you're asked how many atoms are in a certain number of moles, you would use Avogadro's number. If you're asked how many moles from a certain number of grams, you would use the molar mass, or you could do both like we did in this example here. So just another example of dimensional analysis using moles, molar mass, and Avogadro's number.